The next problem we'll work is problem 6 from the study guide in Garrett Biochemistry in Chapter 4. And this problem looks small enough, calculating concentrations of species in amino acid solutions. Calculate the concentrations of all ionic species in a 0.25 molar solution of histidine at pH 2, pH 6.4, and pH 9.3. So I want to say that it is possible to calculate the concentration of all of these ionic species, and that calculation is done in depth in your study guide. However, I'm going to calculate the concentrations of the major species at those pHs, and I'm going to ignore negligible species that would have negligible concentrations at those pHs, because this is a large problem and it would take me about an hour to work that problem on YouTube, if I did all of them. But the calculation for all of them is basically the same, and it is given in your study guide. So you can go ahead and do that if you want, but I'm just going to stick with the major species, okay? So let's get started. Histidine is an amino acid that looks like this. Let me get my thing oriented. Okay. Looks like this. Okay, so we've got a COO minus. This is the standard form of an amino acid, and so we're going to have our R group down here, and our R group for histidine is CH2 plus what's called an imidazole ring. Okay, so at low pH, this imidazole ring will be protonated. Okay, and so it's going to look like this. So if you'll remember from organic chemistry that, or you should remember from organic chemistry, let's draw the unprotonated form of that imidazole ring. So let's just kind of put a connector there to say this is where the imidazole ring is connected. That's this spot right here. Okay, I'm not going to draw the whole amino acid, just the ring. Okay, and so let's look at what this molecule looks like unprotonated. Okay, because I didn't see that online, so I want to go ahead and point that out. Okay, so this molecule, this nitrogen over on the left, is a little bit different from the nitrogen on, and I'm missing a carbon on this. I'm sorry. I need to redo this. A little bit different from the nitrogen on the right. I didn't draw them correctly though, so that made them look very similar. Alright, so I'm just going to ignore that connection and just draw the, oh, this is irritating. Just draw the imidazole ring itself. Okay, and we'll look at the structure of this molecule. So remember that nitrogen has, in its neutral state, 3 bonds and a lone pair. Okay, so let's look at this nitrogen on the left over here. This nitrogen is double bonded to this carbon next door, okay, and single bonded to the carbon above it. So it has 3 bonds. That means it has a lone pair. That means it has a lone pair sticking out. Now this nitrogen on the right, okay, it has a lone pair because it has 3 single bonds, but that lone pair is not connected to the hydrogen. It's going to be up in the ring, and that's going to give, I have drawn this bottom one incorrectly as well. That would not be aromatic. Okay, so that's going to give this this ring aromaticity. So this ring is actually aromatic because that nitrogen can orient itself with the ring, with the pi system of the ring. So if we look at that nitrogen head on, okay, then it's going to have a lone pair here, and this is a 5-membered ring, so let's just draw the 5-membered ring. And so 2 atoms away we've got this nitrogen, and the rest of them are carbons. Okay, so where is our pi system? It's going to be above and below the plane of the ring, connected to say this is, let's number these atoms. 1, 2, 3, 4, 5 atoms in the ring. 1, 2, 3, 4, 5 atoms in the ring. Okay, so atoms 2 and 3 are double bonded to each other. They're donating 1 electron each to that pi system that makes that ring aromatic. And carbons 4 and 5, atoms 4 and 5 are double bonded to each other. They're donating 1 electron each to that pi system that is, let me circle these so we don't get confused with bonds here, that is in the ring. And so the nitrogen in the front here has a hydrogen on it, okay, and that hydrogen is perpendicular to the plane of the ring. So the lone pair on the nitrogen is able to overlap with the ring, and that gives it 6 pi electrons, which is a Huckel number, so we have an aromatic ring. Okay, so I wanted to point that out because I saw some inaccurate information on YouTube. This nitrogen on the right is not the one that's picking up a hydrogen. If it were picking up a hydrogen, it would break the aromaticity. But this nitrogen on the left, and now here I have, it's donating 1 electron, so nitrogen on atom number 3, that nitrogen, is donating 1 electron into the ring. Okay, let's get rid of that. Alright, and so that means it has a lone pair that's sticking out perpendicular to the ring. That lone pair that's sticking out perpendicular to the ring can pick up a hydrogen, making this nitrogen positively charged, and that will allow that ring to become protonated without disrupting the aromaticity. So I just wanted to be clear which nitrogen is picking up that hydrogen. It's not the one on the right. It's going to be the one on the left, because I did not see that information clearly anywhere on the internet. Okay, so let's not forget our organic chemistry as we move along. Alright, and so I've drawn the imidazole ring at the top, and this is going to be at low pH. Okay, and then we're going to have our first pKa, or our pK1, and we're going to have this species here. So we're losing on pK1, we're going to lose, oh, did not mean to have that either. I am making a lot of mistakes here. Really should redo this. Okay, we're going to lose this hydrogen here. Draw our imidazole ring in again. Now at low pH, that nitrogen that we talked about is going to be protonated. Okay, but that ring is still aromatic. Okay, so what charges do we have? Over here on the left, we've got, let's go ahead and get rid of this stuff. Don't be in the way. Okay, over here on the left, we've got 0 on the carboxylic acid group, +1 here on the alpha amine, and +1 in the ring. So that's going to give us a +2 species. So we'll call this HIS for histidine +2. Okay. Now our next species has a +1 in the ring, +1 on the alpha amine, and -1 on the carboxylate. So these two guys cancel each other out, the carboxylate and the alpha amine. Okay, and so there's +1 in the ring, so this is going to be his +1. Okay, now our next pKa, we'll call that pK2, is going to be at 6.0. The first one, I'm sorry, was at 1.8. Okay, and so then the next one is at 6.0, and that's where we're going to lose that nitrogen in the ring. And this is all determined experimentally. It's probably easier to look these numbers up than to try to guess which one is which. But it matters, and that's why your book is asking you to, you know, describe all of the species in solution at these different pHs. If anybody wants to buy a surface Did I get that correct? Yeah. Tablet. I do not recommend it. This is not, and I did not get that bottom one correct again. Okay. And then the next one. Okay, so this one has a +1 on that amine group, -1 on the carboxylate. Okay, and we've lost the +1 in the ring, and therefore we are at 0. So this is our isoelectric species. It's going to be our His0. And then our pK3 is going to be at 9.2. We've got our COO-. I'm going to draw this one down a little bit so that thing will stop popping down at me. Okay, so this one, and I drew that wrong as well. This one has lost the hydrogen on the amine. Okay, so let's back up. Let's call that. So that one is going to have what? It's going to have a negative charge. This is His -1, just from that top carboxylate group. So on the first species, the His +2, we're going to have positive charge on the, a different color here, on the alpha amine and the nitrogen in the ring. Okay, then His +1 here, our second species, is going to be positive charge in the ring, positive charge on the alpha amine, and negative charge on the carboxylate. That first hydrogen on the carboxylate is the first one to come off at the pK1. Okay, pK2, we're pulling off the hydrogen from the nitrogen in the ring. We're losing this guy, and so that's going to be at 6.0. So that's the species after we've lost that one. At our second equivalence point is going to be a +1 here, -1 here. So that's going to be our isoelectric species. Then at the pK3, which is 9.2, we're going to be losing that NH3+, and that's going to leave us with just one negatively charged species. That's going to be His -1. So if we wanted to draw a quick titration curve, we could. I'm going to draw this real small because it's really not relevant for this this exercise. I'm just going to sketch it real quick. So that's 0.5 equivalents of sodium hydroxide or strong base. 1, 1.5. That's supposed to be a 1.5. 2, 2.5, 3. Okay, and our pH is going to be 2, 4, 6, 8, 10, 12. Okay, so at a pH of 1.8, we're going to have a pKa. So our first half equivalence point is going to be our pKa1. A pH of 6 is going to be our second half equivalence point, and that's going to be here. And our third half equivalence point is going to be at 9.2. And so like here, and so those half equivalence points are going to be level. At the equivalence point, we get a sharp increase, half, and then sharp, and then like that, and then we get a final increase like that at 3. So that isn't perfect, but that's basically what our titration curve would look like. Okay, so let's see if we can solve this problem. Going back to the problem, calculate the concentrations of all ionic species in a 0.25 molar solution at three different pHs. pH 2, pH 6.4, and pH 9.3. Okay, so our first one is pH equals to 2. So how are we going to do that? We've got a 0.25 molar solution, and this is pH equals to 2. Okay, so at pH 2, let's just go back up so I don't have to redraw these structures. Let's just go back up. Okay, at pH 2, we're at low pH, so our predominant species are going to be we're going to have a competition between this one on the left. Here, we're going to have a competition. Let's call these species A, B, C, and D just just for ease. Okay, so we're going to have a competition between A and B. Okay, C and D are going to be negligible. So at pH equals 2, our pK1 is 1.8. So we're going to have this competition predominating. We're going to be losing this hydrogen here at pH 2. So we're not going to be fully, this is a weak acid, we're not going to be fully deprotonated. So we're going to have a competition between species A and B. C and D will be negligible. So let's see how we will calculate the concentration of species A and B. Okay, so pKa, or pH, is equal to the pKa plus the log of A minus over HA. Okay, that's our Henderson-Hasselbalch equation. So this is our HA, A is our HA, and B is our A minus. So HA is our His 2 plus, and our A minus is our His plus 1. Okay, so this is our, let's just go ahead and erase this. His 2 plus, and this is our His plus 1. Okay. Alright, so we know the pH and the pKa, so we can use that to find our concentrations, because we also know the concentration of our solution, so that we could say HA plus A minus is equal to 0.25 molar. So those are concentrations. Okay, so the His plus 2 plus the His plus 1 is equal to 0.25 molar. Okay, so what can we do? Let's use our log information, and we can say then that His plus 1 over His plus 2 is equal to 10 to the pH minus pKa. And we had this formula previously. Alright, and so that's equal to 10 to the 2.0 minus 1.8. Okay, so I'll solve for this right here. And that's equal to 1.58. Okay? So our concentration ratio is equal to 1.58. So we can say that our His plus 1 is equal to 1.58 times His plus 2. Okay? And we know this right here, right? Alright, so we know that His plus 2 plus His plus 1 is equal to 0.25 molar. Okay, and so we can take this His plus 1 and plug it in right here. Okay, so we can say that 1.58 times His plus 2, and we can plug it in here. So His plus 2 plus 1, not correct, 1.58 times His plus 2 is equal to 0.25 molar. Alright, so 2.58 times His plus 2 is equal to 0.25 molar. So now we know the His plus 2 concentration is equal to 0.25 divided by 2.58. Okay, and so that's 0.097 molar. Alright, and so now we can go back up to this previous equation. We say His plus 1 is equal to 1.58 times His plus 2. So we know the His plus 2 concentration. Now we can say, let's go back up. His plus 1 is equal to 1.58 times His plus 2, which is 0.097. Okay. And so that is going to be equal to 0.153. Okay. So then we can say that at this lower pH, our His plus 2 is 0.097 molar, and our His plus 1 is 0.153. And so let's say this is pH equals 2. Okay, we've got this right here. Now I would say C is negligible and D is negligible. Now your study guide actually goes through a calculation for C and D doing the exact same thing here. But since they are negligible compared to these two numbers, I have elected not to do those calculations. They're done in a similar way, and you can look at those if you would like to. But I would say at pH equals to 2, we just have these two species, and these last two are negligible. Okay, so our next pH is 6.4. And so at pH 6.4, the predominant reaction is going to be losing this hydrogen here. Okay, losing this hydrogen on the imidazole ring. So we're going to have His plus 1 and His 0. Those are our predominant species. We're going to have B and C. So His plus 1 and His 0. His 0 is now, let's change our colors here. Let's change our color to like orange. And that is going to be our A minus because we've deprotonated, and His plus 1 is going to be our HA. So that's our new HA and our new A minus. So we've got His 0 and His plus 1. So let's go ahead and do that calculation. Alright, so this is pH equals to 6. Alright, and so we've got pH is equal to the pKa, which is 6.0. Our pH is 6.4. So let's go ahead and add that in. The pH, I'm going to go ahead and write it. The pH is equal to 6.4 plus the log, pH 6.4 is equal to 6.0 plus the log of His 0, that's our A minus for this reaction, over His plus 1. Okay, and we know, same thing we did before, His 0 plus His plus 1 is equal to 0.25 molar. Why? Because this is a 0.25 molar solution. At this pH, we've converted almost everything to these two species. So as we increase the pH, let's look back at our titration curve. As we increase the pH, we've converted almost everything. At our half equivalence point, we've got half this and half this. The species A and species D are negligible at this point. So species B and species C, which is our His plus 1 and our His 0, are the only species that I'm going to consider at this point. Okay, so at 6.4, we've got this reaction because our pKa is 6 for that reaction. Okay, so I'm only going to calculate those two species, even though your book goes through and calculates the negligible species as well. Okay, and so I'm not sure what your if your homework will take that, but if not, you can look at the calculation in the study guide. It shows you how to do it. basically. So his 0 over his plus 1 is equal to 10 to the 6.4 minus 6.0, and that is equal to 2.51. Okay? So we can say that his 0 is equal to 2.51 times his plus 1. Okay, so what I did, I multiplied 2.51 times this species right here to get his 0 on its side by itself. Okay, so now we can plug into our second equation up here. So we can say his 0 plus his plus 1 is equal to 0.25 molar. Okay, and so that we know 2.51 times his plus 1 plus his plus 1 is equal to 0.25 molar. So 3.51 times his plus 1 is equal to 0.25 molar. So his plus 1 is equal to 0.07. Okay, so now we can take this value and plug it back in up here. So then we have his 0, I'm sorry, not here. We're going to plug it in over here. So his 0 is equal to 2.51 times his plus 1, which is equal to 0.178. So I'll keep the color different. I may have to overwrite some of my stuff here. But at pH equals 6.4, our concentration of A is negligible. Our concentration of B is 0.07 molar. And our concentration of C, or our his 0, is 0.178 molar. Okay. So, and then D is again negligible. Should have left room for that. Alright, and so we have, I'm just going to calculate one more. Now your book does go through and calculate A and D at pH 6.4. The study guide does. And it's done the same way. It's just a very long calculation. So at pH equals 9.3, what do we have? We have, going back up, alright, 9.2 is the pKa for this reaction. So at pH equals 9.3, we're going to have a competition between his 0 and his minus 1. So his minus, let's change our color again. Let's make it this purple color. His minus 1 is going to be our A minus, and his 0 is going to be our HA. Okay? So, let's erase that. It's confusing. Okay. So what are we losing here? We're losing the hydrogen off of the alpha amine. So we're going from NH3 plus to NH2, and that's why we've got his minus 1 here, because the only thing charged is a carboxylate group. And we've got his 0 on the left because this is the isoelectric species. Okay, so let's do that calculation. At pH 9.3, I don't know why it keeps doing that. I'm just going to have to go on. We've got pH is equal to the pKa plus the log of his minus 1 over his 0, right? And we know that his 0 plus his minus 1 is equal to 0.25. Okay? So, his minus 1 over His 0 is equal to 10 to the pH minus pKa is equal to 10 to the 9.3 minus 9.2 is equal to 10 to the 0.1, which is 1.26. Okay, so we can multiply 1.26 by His 0 and get His minus 1 on a side by itself is equal to 1.26 times His 0. Okay, so we know that His 0 from this equation here plus 1.26 His 0 is equal to 0.25 molar. So I substituted in for, we'll call this equation B. Okay, so we've got 2.26 times His 0 is equal to 0.25 molar. So His 0 is equal to 0.25 over 2.26 is equal to 0.111. Okay. And we know that His minus 1 from this equation here is equal to 0.126 times 0.111 is equal to 0.140. Okay, so at pH 9.3, we know that our first, so species A is negligible. I'm just going to write over all this stuff with a different color. Species B is negligible. Species C is 0.111 molar, and species D is 0.140 molar. If you want to do the calculation for every species at every pH, you can certainly do that, and the way to do that is shown in your study guide, but I've chosen just to calculate the pH of the major species at the concentration of the major species at each of the pHs given. Alright, thanks for watching.